In the previous lecture, I have discussed the image transform. Image transform, I have discussed the basic properties of image transformation. What are the need of the image transform, and why it is useful for the image processing. I have discussed in the previous lecture the role of transform. I have discussed the role of transform in previous lecture. You have used for the mathematical convenience. First, you have used the any signal is taken in the time domain. You are convolving the time domain, then give after the transformation. This is the multiplication of two signals. You are transforming the signals by using the transform. Here the first role is the mathematical convenience. Second is the extract the meaningful information. Here you have observed a white light by naked eye. Then after the transformation by using the prism, it is differentiated in the 7 colors. There are 7 colors. This is the basic needs of the transformation. Here the transformations, the building blocks of the transformation, you have classified the forward transform, reverse transform. You have taking any signal in the time domain, then you have in the time domain you are taking any signal xt, then after the transformation the signal is going to the frequency domain x omega, and then taking the reverse transform, then you have find out the original signal. This is the basic notation of the transformations, forward transform and the reverse transform. Then the basic function, what are the basic function for the transformations, and the finality of the coefficients, orthogonality. This is the basic needs of the basic function for the transformations. This is the basic function of a transform. You have taken some example mathematical representation. You have taking the x is equal to summation I is equal to 0 to n ci. This is the transform coefficient, and x is the input signal, and the phi is the basis function. This is the simplest notation of the transformation, how to work a transform, and ci is represent a coefficient. This is the mathematical notation of the basic transformation notation. You have x cap, this is a reverse. This is the different image transform. You have studied the different image transform. You have studied the Fourier transform, Walsh transform, Hadamard transform, discrete cosine transform, KL transform, Wavelet transform. These are the various image transformation. Then first of all, you have also know the basics of the Fourier transform. जैसे Fourier discover the Fourier transform. This is a French mathematician and physicist. Idea is given to 1809, and the flow of heat through the object. It is the first application is used in the Fouriers in the heat transformation. And this is the mathematical notation of one-dimensional discrete Fourier transform. You have taken a discrete signal xn, then you have taken the Fourier transform of this given signal. This can be represented as xk. Here the inverse transform of this signal could give the original signal. Here this is xk, and taking the inverse transform to obtain the original signal xn. This is a basic notation of one-dimensional Fourier transform. Then this is the basic mathematical representation of the Fourier transform. This can be also written as, you have also studied in the previous lecture in the class of signal system, xk is equal to summation n is equal to 0 to n minus 1 xn e to the power j 2 pi kn, k is equal to 0 to n minus 1. This xn represents the discrete time signal, and xk represents the Fourier transform of the given signal. Here you have represented the discrete Fourier transform in two-dimensional, then this signal can be represented in 2D. Here this representation is one-dimensional signal and this is the two-dimensional. This is the mathematical representation of the signal, can be represented in two-dimensional, means you have represented in row and column, and this signifies Mn. This is a 2D representation of the signal, and then you have represent the one-dimensional spectrum xk, and this can be represented as two-dimensional Fourier transform of the given signal. This can be represented as fkl. After the transformation of the two-dimensional signal can be represented as kl, fkl. This is the two-dimensional representation of a discrete Fourier transform. Then this is the mathematical representation of a one-dimensional and two-dimensional Fourier transform representation. Here the formula of one-dimensional Fourier transform, this can be represented xk is equal to summation n is equal to 0, n minus 1, xn e to the power j 2 pi n. This is the one-dimensional, this is a two-dimensional. Here this can be represented as row and column. That's why the two-dimensional representation of this Fourier transform. This can be represented as fkl is equal to summation m is equal to 0, n minus 1, n is equal to n minus 1. Here this is the square matrix. The m and n are similar. 250 cross 250 cross image you have taken. That's why you have the dimension are same. Then fn e to the power j 2 pi mk e to the power j 2 pi n l. This is the basic representation of the Fourier transform. After the taking the image is taking the Fourier transform, you have find out the magnitude response and the phase response. This is the basic application of taking the Fourier transform of two-dimensional image is two-dimensional signal. That's why you are taking the two-dimensional Fourier transform. Image is two-dimensional signal. That's why you have taken the two-dimensional discrete Fourier transform. Here the basic representation of the Fourier transform. Then importance of the phase. This is the application of the Fourier transform. You have find out the phase and frequency amplitude response. This is the uses of the Fourier transform to find out the phase. You have taken the image A, taking the Fourier transform of the image A, you have find out the magnitude as well as phase, and taking the second image you have denoted as B, and Fourier transform of this B image you have magnitude and phase, then combine it. This is the pictorial representation of the images. You have taken a original image, this is a cameraman image, this is the another image, this is denoted as B image, this is Lena image. After the transformation, you have find out the image after the phase reversal. Here you have two images are being merged, and after this effect, you have read the image A. This is the you have taken as a cameraman image, and you have read B. Read image B is a Lena image, and after the manipulation, the cameraman after the phase reversal, इसमें आप phase reversal कर दिए. देखिए इसमें background आपका लेना में कुछ आ रहा है, ठीक है. इसमें आपका लेना आफ्टर द फेज रिवर्सल कर दिया, तो उसमें बैकग्राउंड में आपका कैमरामैन में लेना के कुछ फेजेस आ रहे हैं, कुछ एजेस आ रहे हैं. दिस इज द एनालिसिस, दिस इज द इंपॉर्टेंस ऑफ द फेज इन द इमेज. दैट्स व्हाई यू हैव गिवन दिस एग्जांपल. Application of Fourier transform and the image processing. You have uses the different types of filters for the image processing. Simply you have taken the block diagram of simple. You have taken the FM, the simple image. After the filtering, you have obtained the GMN. FN is the input image. HMN is the impulse function of this filter function, and this GN is the output image. After the filtering operation, you are convolving the two signals. GMN is the response of this filter, is FN is the convolution of the HN. This gives the response of the signal system. And this application of the image processing in different fields. You have convolution of time domain, multiplication in the frequency domain. This is the basic use of transform, image transform. You have taken the DFT of this signal, and this after this the inverse you have obtained the original signal. Another use Walsh transform. This is another transform. This is the Walsh. It is a mathematician. You have invented this Walsh transform. That's why it is the Walsh transform. And this is the basis function of this Walsh transform. Here 1 upon n. So, I is equal to m minus 1. This is the basis function. This is a complex basis function. Here it is a logarithmic basis. N is the time index, k is the frequency index, n is the order. Here the various bases of this Walsh transform. The Walsh for the n is equal to 4. What are the computations for this computing the basis function for the Walsh transform? This is the tedious mathematic computations. After there are various steps to compute the Walsh transform basis function. I have given this slide to understand the basic steps and mathematics of the computing the Walsh transform basics, and just glimpse about the what are the mathematical formula of the various image transform and what are the applications of image transform in the image processing. This is the basic mathematical representation. I'm not bothered about the basic mathematics. I'm just giving the uses of the transforms in the image processing. Here, using the decimal number and the binary representation of this image, what are the mathematical representation of this image, and this is the matrix representation, and this represent the sign changes in this matrix. This is a basic function, basis function of this Walsh transform. This is a standard basis function to signify the basic operations of the Walsh transform. And the number of overlaps of 1 in odd, then sign is negative. This is the basic representation of how to change the basis, represent the overall operations. Another transform is Hadamard. This is the another transforms. This is invented by Hadamard, and this is the matrix of the Hadamard basis function. How it works? H to n. This is the hn. This is the diagonal. These are same. This h2 is the standard basis function, 2 cross 2. This can be also represented. This is standard. This is the Hadamard basis function. This is the basic criteria for the Hadamard basis, and what are the basic properties of Hadamard. I am not giving the detail. I am just giving the brief introduction about the basis, different transforms. Then important transform is the discrete cosine transform. You also know the discrete Fourier transform. Then you have also, this is the modified form of the discrete Fourier transform. It is invented by Ahmed, Natarajan and Rao in 1974. Discrete Fourier discrete cosine transform. Here only cosine basis function exists. Here the cosine kernel basis function. This is a two-dimensional. That's why it is represented as a the Hadamard discrete cosine transform, because this is very powerful transform, discrete cosine transform. It is used for JPG compression algorithm, joint picture expert JPG compression, lossy compression. That's why the DCT is most popular transform for the compression purposes. That's why DCT is most useful transform for the compression purpose. And the basic formula of the discrete cosine transform. Here this is a two-dimensional discrete cosine transform. There you have represented FKL, alpha and alpha k and alpha L is the coefficient constant. Here this Fn, this is a input image, cos 2 pi m pi k 2n cos 2n plus 1 pi L upon u. This is the basis function. Here discrete cosine transform has only cosine function. That's why it is a discrete sinusoidal arbitrary transform. And the discrete cosine transform had a unique property. It is energy compaction property and unique diagonal properties, highly energy compaction. That's why the DCT transform is widely used for the image compression. The DCT, the another separability property, there are various property of this discrete cosine transform you have used for the lossy compression. So this is the discrete cosine transform formula, and the properties of the discrete cosine transform. First is the real and orthogonal. Discrete cosine transform real and orthogonal, and DCT has excellent energy compaction property for the highly correlated data for the following reason. Highly energy compaction means fewer coefficient define the whole image information. That's why is the high energy compaction is the all the transform has energy compaction, but the DCT has high energy compaction property. The one more silent feature of the DCT is separable property. You have separated by row and column. Separable property of 2D discrete cosine can be computed to separate one-dimensional transform, 1D row and 1D column of the images. You have separately find out the 1D row and 1D column, separable property. ठीक है? So you have first is the real and orthogonal, and another is basis vector of cosine transform are eigenvector of the symmetric trigonal matrix. It is a one unique property of the discrete cosine transform कि आपका जो आइगन जो DCT का बेसिस वेक्टर होगा उसमें आपका आइगन वेक्टर ऑफ सिमेट्रिक ट्राइगोनल मैट्रिक्स, उसके जो ट्राइगोनल्स होंगे वो यूनिक होंगे, सिमेट्रिक होंगे. ठीक है? जो आप देखेंगे मेटलैब में, आप कोई इमेज लेंगे, उसका डिस्क्रीट कोसाइन ट्रांसफॉर्म निकालेंगे और उसमें देखेंगे कि जो आपके उसके आइगन वेक्टर होंगे वो सिमेट्रिक ट्राइगोनल्स होंगे. मान लीजिए 1 माइनस डी 0, तो आपके जो डायगोनल्स होंगे सिमेट्रिक होंगे उनकी वैल्यूज. ठीक है? तो ये दिस इज द यूनिक प्रॉपर्टी ऑफ द डिस्क्रीट कोसाइन ट्रांसफॉर्म, एंड दैट्स व्हाई discrete cosine transform can be used in the various fields. First is the lossy compression. It is used for the lossy compression, and it is used in lossy compression means it is a class of used in the JPG, joint picture expert group. The algorithmic approach you have uses the for the transformation for the compression you have used adopt the discrete cosine transform for the compression purpose. So that's why DCT is the most popular transform, image transform for the compression, so on, and the various applications of the discrete cosine transform in the various fields. It is the basic property. DCT is the techniques converting signal in the elementary frequency components and widely used in image compression. That's why the discrete cosine transform is preferred instead of discrete Fourier transform. Widely acceptable for the compression purpose. That's why the DCT is used. क्योंकि आपका DCT आपके कंप्रेशन, इमेज कंप्रेशन में यूज होता है, उसकी हार्डवेयर या फिजिबिलिटी है. दैट्स व्हाई DCT इज मोस्ट पॉपुलर इंस्टेड ऑफ डिस्क्रीट फोरियर ट्रांसफॉर्म, क्योंकि आपके उसके हार्डवेयर और उसके एप्लीकेशंस, आपके जो एल्गोरिथम एग्जिस्ट हैं कंप्रेशंस के लिए, वहां डीसीटी को सपोर्ट करते हैं, डीसीटी को अडॉप्ट करते हैं फॉर द कंप्रेशन पर्पसेस. दैट्स व्हाई डीसीटी इज प्रेफरेबल. Another transform is also used for the compressions, but some shortcomings are disadvantage of DCT. And another transform, the advanced compression algorithm JPG 2000. Another compression you have uses the wavelet transform also for the compression. High compression ratio are used. JPG 2000. Another compression formats standards are used. Wavelet transform for the compressions. But essentially, DCT is more popular. That's why it is more preferable instead of DFT. This DFT is easy but not. ठीक है. That's all.